Shall we start? Mayor, did it start? Oh, everyone, wherever you are on this planet. Today I would like to present two things. First, an update about what I'm doing around the build called Abio Flex Wanderer. Okay. It's closely done with Meyer, but we have two different robots and also two different personal goals. A lot in common, but a lot personal goals. This will be relatively fast, and for different reasons I will explain. And I have a second presentation, if we have time, which is to talk about something called abduction reasoning. And the goal is to talk about the technology and also to talk about why it may matter for what we are trying to do. Anyway, I will just start with the updates. So on this build, I'm going to review a bit what has happened since the beginning, which is back in January, basically, on this build. Okay. On the different things I wanted to learn, and I hope that some people join to learn together, and also some of the achievements I'd like to set forth with this build. Okay. And so there are mainly 3 points. Okay. The first thing I wanted to do is to have a remotely accessible test bed. So I will detail what this is concretely now, because it's running since basically March. Okay, and this was more to foster collaborative work, and it was before the COVID. It's justified with even more with COVID. Okay, but it's more to foster collaboration remotely. When as we know that boats can be relatively expensive depending on what kind of hardware we are using. The second point is about basically a software middleware. Okay, we've talked about that several times in these weekly discussions. Okay. And here I'm talking about something that I call Boss. I will justify why it's called Boss. And this was actually the first thing I presented in January, when joining the Yak Rover project. The third point I will talk about, that's something that is my real intention, okay, is to have autonomous rovers, as much as it matters, basically. Okay, so first on the remote okay, so first about the state, okay. So the test bed is available. You can connect to it. You just ask me, and I can grant you access to it. It's done, but when it works, because right now it's down, because I had a problem that is on the chat, where I just broke physically the operating system. Okay. And the others, so the software part on Boss and Autonomy, these are work in progress with different stage of advancement. I will talk about that later. Okay, so the test bed. Okay, so you can see on the central picture a blurry image of how the boat looks like. Okay, so it has 6 legs. It's 18 sabots. Okay. It's pretty simple, pretty straightforward, but also pretty convenient to use. Okay. Also, it's relatively powerful. It's a Raspberry Pi 4 with 1 gig of RAM. And this particular build is extended with several extra hardware that look interesting to experiment with. In particular, it's I had a previous session where I talked about multi-compute boats. Okay, so it's a rover with several CPUs, basically. And so this is where I was introducing a camera called the Hawk One, because that camera contains a full computer inside it, to which you can delegate specialized computation, like, for example, object detection, stuff like that, so that your main computer can focus on the safety critical part of the rover. And it turns out that it's also to mimic what is done in in rovers like Curiosity and Perseverance, okay, which are multi-computer rovers. It's hard to see on the picture right now because it stands on a table because I was experimenting with an Intel RealSense camera. But the thing that usually the boat is on the floor, just under. We can see where there are pictures of a Martian soil, okay? And so when it's there, there is about a square meter or the 3 square foot available to move around, okay? And to bump into things if it matters, okay? Because it does matter in some of our experiments. And so it can remotely be piloted this way. And to anyone who would like to experiment with such kind of rover. Also, from the very beginning, it was a streaming. It's a video stream from the camera. And you can access the stream and also take snapshots. And that has been upgraded by the work from Meyers, where he integrated all that with Twilio, as we've seen in his live demo a few months ago. And so it's available on this boat as well. Also, I have extra hardware that I bought and put on this rover. They are unplugged right now, but I can put them on demand if someone is interested. It's an Intel neural compute. Okay, so it's a USB extra CPU to do basically matrix computation more efficiently. The Intel RealSense that you can see in the middle picture, and OGD, which is a bit like the Intel RealSense, just an alternative and cheaper build. So that's the test bed. So again, you can access it, and you can access to a Raspberry Pi with a Raspbian. We have a large disk, 256 gigabyte to put programs and to experiment. So if there is interest, really, anytime you can ask on Discord. So that's done. That works most of the time. The second point was about a software library that I call Boss. Okay, so the name Boss is just a kind of pun because it's the yak, the animal, the yak, is from a genus called the Boss genus. Okay, and that sounded like Ross. Okay, and it's there is a lot of coverage. Okay, so it turns out that the Boss, in the way I approach it, is basically conceptual. It's a concept. That is to say, yeah, we need a middleware, basically. A rover is a kind of specialized tool to some extent, okay? And so we shouldn't be reinventing the wheel all the time. So Boss may be Ross plus something else, may scavenge Ross. I don't know, I have no decision on that. Okay? So here I'm just explaining about the intent and the framing, because I see that there are a lot of differences with Boss. Okay, so the goal, okay, is to have a lot of facilities to so that we can make interesting software, so mission software, without reinventing the wheel each time. Okay? And there is a specific focus on mobility, because a lot of things depend on that, but it's not limited to it. I use mobility because it's fundamental for us. And a lot of the middleware for mobility would be useful for other aspects, like, for example, sample manipulation and stuff like that. Okay, so there is a specific interest I have where I do not have any answer. We'll talk about that in more detail. It's about a generic API, so generic software, to talk about motion, okay, to ask for motion. So in the image here, you can see we have okay, a path from A to B, okay? And so how do we ask a rover to follow that path, basically, okay? How do we do that simply with the software when the rover has wheels, when he has legs or wings, okay? Or maybe it's swimming as well, okay? And a question that looks so simple that sometimes I'm ashamed is that what does it mean to go forward, okay? And I've experimented on trying to make something generic of what it means for something to go forward, and I'm not decided, okay? So I will skip this discussion because I'm not even sure it's really useful, because we can skip it because there are so many rovers that can go forward anyway, okay? But I wonder whether there is not something interesting. So for me, it's a kind of a side discussion. It has become a side discussion for now. So here I describe, I take back this slide from January. Okay, this was my my intention. It's more about to detail the difference with systems like ROS, basically. So at the bottom we have a hardware which is uh, um, a rover, okay, on which we are running some operating system. Okay, so right now, because I'm asking for an operating system, I may be excluding completely microcontrollers. Okay, so that's one of the limitations of the thinking, but I don't want to be too much constrained by the hardware here. And so on top of the operating system, I put this yellow box called the Boss middleware. Okay? And this is more or less what ROS would be. Okay, ROS would be this yellow box. And so this yellow box middleware means a lot of facilities to make applications more convenient and more repeatable. Okay, it's exactly what we see in the ROS2 ecosystem, where it's getting more and more streamlined. Okay, so that for big companies to for their very specific scenarios for robot in warehouses and stuff like that, they can streamline all the development for that in a much more efficient way, at least in their point of view. Okay? But here there are two other boxes, the blue and the green one. Okay, and so the names evoke something that now a lot of people talk a lot about. It's about this book called Thinking Fast and Thinking Slow, or something like that. Okay, where basically thinking fast is a system one thinking. Okay, where basically it's what our body is doing all the time. Okay, it's our reaction, it's our reactivity to support survive, to survive and so on. Okay, and there is system two thinking, which is much slower, which is when we think, is where we use mostly symbols. Okay, to do mathematics, to planning and things like that. Okay? And so these boxes, they are not directly available in systems like ROS. Okay, still there is a lot of work that is done separately from us. And one of the very interesting parallel is with something that a lot of you are familiar with or became familiar with because of this project, is the subsumption architecture, okay, which was introduced in the late 80s by Ronnie Brooks at MIT, where basically he was structuring the brain of its robots in layers of more and more abstract at more and more abstract levels. Okay, and we see a direct mapping with the system one and system two kind of thinking. Okay, so this graph tries to capture the what we've learned to some extent from the subsumption architecture and from the system one system two split. Okay, and so I will skip on the boss advisors. Okay, but that was back in the former presentation, and you have the link at the bottom of the slide. Here, I'd like to map to what's happening on our spiders. Okay, is that we have a concrete example here in where we are going. Okay, so the hardware is a board. Okay, the operating system is Raspbian. Okay, so it's the Raspberry Pi version of Linux. Okay, and on top of that, the middleware is a set of drivers, to control the servos, and several adapters and extra things like a time sharing. Okay, it's something that actually Meyer and I would like to have. It's the ability to use to multitask on a boat by time sharing. Okay, but these are ideas we are trying to explore. And on top of that, we have the system one. So here, system one concretely, what it means is a set of primitives. Is to go forward. To go forward for a spider is different than to go forward for a wheeled rover. Okay, why? Because when we execute a command like forward, the way it's translated into actions is different. Okay, just turning a motor for wheels, or coordinating several servos for a wheel is different. Okay, so these are different system one APIs. And on top of that, we have behavior. So system two is where there is some kind of thinking. Okay, where we have scenarios to go from A to B or to define goals, and this is where part of the autonomy comes into play. Okay, so the situation right now is that what you have in the red circles, so behaviors and the middleware part, is what we are actually working on So when I say we, it's on my side and together with Meyer. Okay. And in the middle, there is these primitives like forward, backward, and turn. Okay. And so these ones, from my point of view, they are much harder than they look. Okay, surprisingly. Okay, and from my point of view, it's on hold. And what I mean by that is that I'm just using let's say, straightforward definition of what forward means. Okay, I'm not trying to expand more on what I'd like to be exploring on what forward actually means for an agent. Okay, so that was about the boss part of the work. Okay. Please interrupt me if there is any question. The last point is about autonomy. Okay, so the third point of that I like to address in this project, in the long run, I would say. Okay, and here I will simplify the discussion to just the autonomy of navigation. Okay, because just for sake of time, because I think it illustrates enough. Okay, so the second bullet shows it's ideally in a Boss system 2. Okay, so it's the top of the pyramid. If you see it, it's about the behaviors. Okay, it's not a definite answer, but it's how I see it right now. Okay, because the idea would be to have, a software API where you just say, okay, we just state the destination. Okay, so go to B. Okay, and we don't want ideally we don't want to explain the rover step by step how to go from A to B, even if something happens in the middle. Okay, and so here there is an example with the image where we want to go from A to B, and the robot has some plan, which is this path. Okay, and we know there is a rock on the way. Okay, and we have some data about these rocks. But if it's happening on Mars, maybe we don't have enough resolution to know whether this path is actually feasible or not, or whether it will hit the rock. Okay, and that's the kind of detail that, as much as possible, we would like to delegate to the robots for challenge, but also for practical reasons, because Mars is pretty far away, and it takes 50 minutes just to send a message. No, just for a message to arrive there. Okay, so how it's solved right now, and this is actually a transition slide to the next talk. Okay, it's about if we talk about autonomy in a navigation. Okay, what is done is with something called planning. Okay, so planning is something very well defined. Okay, it's the dynamic creation of a plan of action that we want to execute in sequence or in parallel. Okay, and so when there is any kind of problem, usually we are just doing replanning. And how we do replanning? Usually we break down into that. You can imagine curiosity going somewhere and there is a problem. And so when there is a problem, it just stops and asks humans what to do. Okay. And so there is some work done around that, okay, to make it more flexible. Okay. And now NASA is using more and more the word semi-autonomous. Okay. And I will talk about that a bit later. Okay, but what I would like to do with this project, okay, so it's to see whether we can have more autonomy, okay, and in many ways, in many practical ways, be more useful in terms of space missions, but maybe also when going back to Earth applications, perhaps here too as well. Okay, so this is where we talk about artificial intelligence, we talk about deep learning and things like that. But something we don't talk about much, but that is coming back, okay, it's something called abduction reasoning, okay? And there is, as far as I know, there is nothing really practical done with that. But it's something I'm working on here, and I will explain later more about that. And so you have a link here to that presentation. And if there is interest, I can give this presentation right now. But that's it for the updates. But wait a second. There is, yes, okay. So that's it for my update about what has been done, what I'm doing since my last update. It was a couple months ago. Would there be any question or any interest to dig into one of the three topics?
I'm curious to hear more about the abduction reasoning thing.
It was a bit designed for that. Any question, or do I just move on?
I'm kind of curious what the software library boss looks like. Like, I think maybe I missed one of your original talks, maybe where you went deeper into it, but I don't know. I'm kind of curious what it looks like.
Yes. So first, I will not hide here. There is not much, okay, because I started to work on this box, the primitives to go forward, backward, and to try to define that. Okay. So there is code that it's on GitLab, but honestly, it's not super interesting because it's publicly available. Huh? It's just because I decided a few months ago to wait for that because I'm not ready. I don't really know where. I think there is some kind of value in what I'd like to achieve, but I still don't know how to achieve that. Okay, and so the rest of what I call Bossa is the yellow and the green box. Okay, so about the behaviors in drivers, and that's still very fragmented. I didn't put it into the Boss repository. So when you did your presentation about Stubborn, okay, about what you've done, and you also shared, your link on GitHub, and we started a discussion. Sorry, I think I did not follow up on one of your questions there, okay, where you're talking about such kind of matters. Okay, that's why I'm pretty interested. Okay, it's the kind of thing that I'd like to explore more. Okay. But currently, it's more about the yellow and green box for practical reasons, because I was expecting to show actually more concrete result this iteration, but it will have to wait the next one. I broke a few things and still lacking data to demonstrate what I'd like to demonstrate, especially inside the green box.
Yeah, and I'll note that GitHub thread hasn't had any updates since, because I realized that the general sense of what forward and backward is actually kind of a hard question. So I agree. I'll just skip around it myself as well.
Yeah, but you see, if you also see there is something happening there, maybe there is signal to exploit. Okay, I don't know.
The system 1, system 2 concept I hadn't thought of before. I think you maybe brought it up in that thread, or but that was very helpful. Yeah.
Oh, great. Okay. In the thread, I talked about the subsumption architecture, but I try to explain here that there is a mapping, basically. Okay, it was not conceived that way back then. Okay, but the mapping looks pretty clear. But anyway, on the forward backward, the definition in an how to say generic way, it's on pause right now, but I hope I'm not giving up, because there's something here.
I have a question. I notice you have the boss advisors on the left, but not on the right. What are the plans for that?
Yes, because the intent of the slide is just to show what's actually happening. Okay, it's and so the boss advisors on the so the left is more the abstract stack that I'm that I have in mind just as a loose guide. Okay, and on the right one is the experiments we are conducting on the Hexa board. Okay, and so the boss advisors. The thing that in our discussion, several of the boss advisors became part of the middleware. So it's something like time sharing and what I call the self. Okay, is for the bot to have some awareness of itself for things like auto diagnosis and stuff like that. Okay, and to detect, oh yeah, so one leg is broken, so maybe we need to lift it up and move to a 5-leg motion mode, something like that. Okay, and so those are, in terms of software architecture, I see them as services. Okay, that are sitting somewhere on the system, okay, as a boss advisors. But on the right hand side of the stack, okay, it's some of them are merged inside the middleware, basically.
I have a
So-
couple of comments on the what going forward is, quick ones. One is that there's interesting anthropological data on different human cultures that have different conventions for talking about right and left. So most of, I think, the big civilizations, they have body referenced notions of right hand and left hand based on, like, right-handed and left-handed, and forward is where you face forward. So both the bodily asymmetry plays a role in orientation for rotation, and then the face forward plays a role in orientation towards north. But there are some tribes that use absolute orientation. I forget the references, but they're like, north, south, east, west, that kind of orientation rather than left and right. And an even more interesting one, I think it's a tribe in Papua New Guinea or something, where the reference system has to do with a river that flows from the top of the island to the ocean. So, river towards the ocean versus river uphill. So there's like multiple orientation systems you can use that are global, local, but external, and then personally body centric. And connecting that to the other comment I wanted to make, which is when I was designing my rover in CAD, I realized I was actually getting left and right confused. And that's because in CAD programs, there are two basic representation schemes called, I think, first and third quadrant views or something. I've forgotten. It's a long time ago that I learned. But basically how you do the projection and the conventions. And depending on which convention you use, the body left will be the left-hand view of the drawing, or the body left will be the right-hand view of the drawing. And as it happens, the Onshape CAD that I'm using, what the CAD program tells me is the right-hand view of the rover is actually what from the body-centric view would be considered the left-hand view. Now, these confusions, the reason I'm bringing them up is I think if you want to get a well-posed notion of like forward, right, left, and things like that, you should probably start with understanding what are the symmetries and how are they broken in the body of the robot, because that's how biological creatures also tend to do it. And the only time you would not do that is when there's something much more powerful overriding it. Like if it's a flat plains kind of tribe, probably left, right, and face forward is the right orientation scheme to use. But if you live on a very steep island where the ocean direction and uphill direction are extremely important, there's a good chance that that external reference system is actually more important, right? So there's like some taste and aesthetics and like heuristic efficiency involved there. But the body-centric one is interesting because, like for example, the six-wheel rocker bogie, the only symmetry break is in fact the bogie, back and forward. And I kept finding myself getting confused of what's forward, what's backward. And I ended up sort of making up a mnemonic that the nuclear reactor on Curiosity and Perseverance, that's the back and the other is forward. But you can't actually tell because, for example, the motion is more efficient in the nominally backward direction. So there's all these sort of things. So it's, I think, some of the interesting, these may not be central to what you're exploring, but they've been on my mind as sort of peripheral to the phenomenology of, body-centric chirality, left, right, forward, and what asymmetries and symmetries you can exploit to define useful things, because the environment may not be symmetric. If your spider bot, one of the legs breaks, it may break the symmetry with reference to which, the body-centric forward is defined. If in my six-wheel rocker bogie, maybe the camera gets stuck facing backwards, maybe I should redefine forward to mean backwards, because maybe the right way to define forward is whichever the way the camera nominally faces, right? So there's, I think, a lot of interesting phenomenology there. That's not quite tied to maybe what you're thinking of, but I thought I'd throw that out there. Sorry, went on too long.
No, thank you. So it's completely related, Venkat. Thank you. Sorry, someone else was trying to ask a question, maybe?
Yeah, are these boss advisors human advisors, or are these some sort of software?
No, it's a software. Okay. So the idea is to have, I think one of the closest image is a kind of system services you have on many operating systems. Okay, it's software processes that are running all the time, and that are reacting to some events. Okay, so these are software. I should maybe open because, to be honest, I have some doubts about my memory suddenly. Because I did reread my slides to try to make something compact, but okay, here the rover advisors. Okay, so here I think I'm talking too much into software terms, ability to specialize. How can I explain that? Yes, so one example of a Bossa advisor is, for example, if our rover must maintain some guides, okay? So typically you see on our spider, we have the main body is pretty large, okay? It's a kind of a hexagonal body, okay? And we may have applications when we want that body to be flat and always flat, especially when walking, okay? And when I say always flat, it's mostly flat, okay? And so this kind of guide controller, okay, that it's not system 1 and system 2, because here system 1, system 2 is, in this sense, is more about commands, okay? That, okay, we want to go from A to B. Okay? But the boss advisor knows that we are moving stuff around, okay? And so the boss advisor role is to maintain the body flat with respect to the ground, okay? And so anything that happens between the system 2, system 1, and middleware down to the hardware, to go forward, so to control the servo to walk forward, okay? They can be overridden, or they can be constrained by a boss advisor by saying, oops, if you're going that far, we will lose guide, the guide will change, so you should do something, okay? Aniraj, is the example good enough?
Yeah.
Would there be any other question? So it seems that there is some interest on the topic of what means going forward and stuff like that. Okay, and I really like the feedback of the two feedbacks I got today. Okay, and I'll be talking more about that later. Okay, and I'll go back to the GitHub discussion to continue what is dangling around over there. We can come back to the different topics, but if you don't mind, I will go ahead with abductive reasoning. Can everyone see the slides? Hello?
We saw them when you asked.
Okay, no, I had strictly no feedback, so I was wondering whether I was still online, honestly. Okay, so abductive reasoning on Mars, of course. And so the expression can be hard to understand, okay? And so before entering this presentation, it's just a slide to explain the intent of this presentation, okay? And so my personal question is why would this thing called abductive reasoning matter? Okay, and by answering this question for myself, I wonder whether it will not be a good perspective for everyone here. Okay? It's something that is old in the AI world, but that we almost don't talk about anymore. Okay? It's coming back with some very specific people, okay, but not so much. Okay, and in particular, I will show the relationship with something called deep learning. Okay? And so the second point is about autonomy. Okay, and so I'm talking about abductive reasoning for that to have more autonomy on a rover. Okay. And so by autonomy, I will simplify the meaning to mean that it's going to work on its own. Okay? So we know that it's not completely true. Okay, it's there is some extent. Nothing works entirely on its own. Okay, but let's simplify to that for sake of discussion. And more specifically, okay, it's the kind of scenario like we want to say to the rover, okay, go get samples at some coordinates and come back. Okay, that's all we want to say. Ideally, we want the rover to do it and to complete the mission, come back, and that's it. Okay. And also in this presentation, I will try to give you information about what exists already, what it is here, where are we? Okay. And so one thing is that most robots and the robots that interest us, like Curiosity and Perseverance, for example, they are not autonomous. Okay, I will show about the thing that NASA called them semi-autonomous and what it means. Okay, but concretely, they are mainly remote controlled. Okay? And also, there are several autonomous functions. Okay, but they are very focused. Okay, which is great. I mean, in terms of engineering, you know, it's there are a lot of reasons to do that. I will explain some of these. Some of those, okay? And the last point is that at present, I'm not aware about any use of abductive reasoning in robotics, okay? I know several projects for decades ago, okay, on robots and so on, okay, but I haven't seen anything getting out of that, okay? Okay, so first, I guess most of you have read the book, The Martian, or perhaps just seen the movie called The Martian. Am I right? So I don't hear anything. Sorry, I need to check whether I'm still online. Okay.
Yeah, we've watched it.
Okay.
No, I have one basic question. What is abductive? Like, what
Yes,
does it
I will come
actually...
to that.
Okay.
Yes. So I will come to that because it has a very specific meaning here. Okay, from the 19th century, just to give you some heads up. Okay, back to The Martian. Okay, so just whether you read it or not, you just know the plot. Okay, is that there is a team on Mars. Okay, and there is a kind of dust storm, and the team has to evacuate. And one of them, Mark, I think his name is Mark. Okay. Is stranded on Mars because the team has to leave, and they don't know about him, but they saw him. They kind of saw him die. Okay, and so we have, in the book, it starts something like the last thing I remember was seeing Johansson, another character, hopelessly reaching out toward me. Okay, and so you can imagine this Johansson seeing a colleague, trying to help. Okay, and because of the dust storm, this character Mark disappears in the dust. Okay, and so everyone thinks, okay, that Mark is dead. Okay? That's the conclusion. That's what we think we know. Okay, and so why do we think so? And so obviously, so we are Houston on Earth, okay, and we've got some report 50 minutes later that Mark is dead. Okay, and so why would Houston think that he's dead? Okay, so first he's not here, so kind of obvious. Okay, but he's not here. But after we add up some more information around us. Okay, we lost contact in the middle of a dust storm on Mars. Okay, it's kind of pretty extreme event. Okay. Also, there are some witness that Mark has been hit or maybe impaled by an antenna. Okay. And also, we have the generic knowledge that humans are not well cut for life on Mars if they don't have all the equipment, basically. Okay, so all these bullets are what we call here evidence. Okay, and all this evidence, we put them together to justify the conclusion that Mark is dead. Okay, so try just to think about this mechanism, and let's play it again a bit more. Okay. Later in the movie, we see a screen like it's on Sol 18, so it's a Sol is a day on Mars, okay? On Sol 18, we have this image of the base from the satellite, okay? And a few days later, Sol 54, we see that it changed, okay? That we see first there is an object that is here that was not there, which is, by the way, a big rover. And we see also next to the red circle that something very dusty becomes very white and clear. These are the solar panels, okay? So what's happening here is that suddenly we have a new conclusion, that Mark is alive. We are still in Houston, but we suddenly have a new conclusion, Mark is alive. Why do we think that? From the pictures I've shown just before, we have proofs that there is human activity on Mars. Someone is cleaning up the solar panel. Someone has moved the rover. Okay. They also mention in the book that there are some emergency pop tents that have been deployed. Okay, and these ones are not automatic. Okay. And also we have the generic knowledge that, well, on Mars, we are not aware about too many people able to drive a rover except humans. And so here you see we have a completely different set of evidence that lead us to conclude, and on purpose I strike this, it's not to conclude, it's to justify going that toward the conclusion that Mark is alive. Okay, so you see here there is a pattern about having a conclusion and collecting evidence to explain that conclusion. And that's the power of evidence. Okay, we often talk about knowledge. Okay, but the evidence is how we use that knowledge. Okay, and you see, in one, depending on the evidence we get, we can conclude one thing like Mark is dead, and we can conclude actually the contrary, that Mark is alive. Okay, depending on what evidence we have selected. And so this is what abductive reasoning is. Okay, it's about it's a mechanism that has been explained, formalized on how to explain that we have this ability as humans to select evidence to the best explanation for something. Okay, and so here best is not a mathematical best. Okay, it's not a provable best. It's to the best of our knowledge. Why does that happen? Okay. And so the second bullet about the textbook example is kind of telling. Okay, it's really the textbooks. It's what we teach when we talk about abductive reasoning. Okay, is that we make some observation. Okay, so the grass is wet. Okay, and we have this knowledge, this evidence that okay, when it rains, the grass gets wet. Okay, so abductive reasoning will allow us to say, oh, the grass is wet, so it has rained. Okay, and so I hope that doesn't sound too ridiculous. Okay, because it's something that is so common, but that it has been formalized only in the 19th century. Okay, while reasoning is from the Greeks, basically. Okay, was formalized by the Greeks. Okay, so we have 19th century between other form of reasoning and abductive reasoning. Okay, so in fact, there is a subtlety here. Okay, because if we say, okay, the grass is wet, and by abductive reasoning, we will say, oh, it has rained, because we have evidence to justify that it has rained. But the thing is, we have no idea whether it rained. Did it really rain, or was it morning dew, or was it a flood that happened and we are just not aware of it? Okay, so abductive reasoning didn't get so much press, okay, because there is something, there is a mathematical property it doesn't have called soundness. Okay, it's not sound. In a way, it's not valid. Okay, but the thing is that we are doing such kind of reasoning all the time. Okay, so there is something very interesting here, is that it allows to reason under uncertainty. Okay, so I hope it's not too mysterious so far, and I will explain more on that with concrete examples. But so far, do you have any question about where we are now? I will explain what abductive means. Okay. Hello?
All good, no questions.
Okay, yes. So, sorry, it's my room is very silent, so I'm just hearing me talking. So if I can have some echo sometimes, it would be fantastic. Okay, so just it's not in the slide. I wanted to put it. I forgot. It's what abductive means. Okay, so the modern, it's not the modern meaning of abduction. Okay, because abduction is kind of scary thing. Okay. It turns out that abductive in the 19th century, when this expression was conceived, formally, okay, I mean the dictionary, abduction means collecting evidence. Okay, it's literally means collecting evidence. Okay, and I couldn't believe that at first. I thought, wow, I missed, because I studied that the first time like 20 something years ago. Okay. And I had a completely different understanding. And it's recently that I got back into, yeah, there is things to do there, okay? And this is where I discovered what abductive really means. It meant back then collecting evidence, okay? And so it means reasoning by collecting evidence, okay? Anuraj, does that answer your question?
Yeah. Yes.
Okay. And so when we hear that, it's some people have such kind of face, okay, that what are you talking about, okay? And so that's why I'd like to have some more, to put all in the context of more concrete example to see where it could have value, okay? Because I still have to do it to prove the value. So right now it's a bit speculative, but with some confidence. Okay, and so here is a quiz. Is that what do you think Sherlock Holmes' main reasoning method was? Anyone wants to try here?
He says deductive.
Yeah. Abducted.
Yes.
I know the answer, so I shouldn't guess, but
Yes.
it's
So
abductive. Yeah.
yes, it's abductive. But the thing is that it has been understood only recently, okay? Because Sir Arthur Conan was born at the same time, well, at the same period as the person who created abductive reasoning, okay? So his name is Charles S. Peirce, okay? An American philosopher who was working at Harvard at the end of the 19th century. And this is precisely when the Sherlock Holmes novels were getting published, okay? And at that time, yeah, it was the power of deduction of Holmes, basically, okay? And you've got books, you've got movies, and so on, where everything is based on deduction. But the thing is that, no, it's actually abduction, okay? And I hope that during this talk, you will see why, okay? Okay, so, let's talk about Mars rovers and where AR can help. And of course, AR doesn't mean AR, okay? So I put it here because it's a shortcut. So please do not think it's augmented reality, okay? It's abduction reasoning. Okay, so let's back to this scenario where we have our rover in A, okay, and we want it to go to B, okay? And so what is done traditionally is that we make a plan, okay, on how to go from A to B, okay? And the thing that, the rovers, they have a local scanners, okay, local cameras. And when they get close to, when they get really where they are, okay, we can get more fine-grained information, okay? And so if there is a rock that we didn't evaluate properly, or maybe that rolled on the way, okay, we would expect the rover to be able to deal with that, okay? By dealing is maybe to turn around it, okay, or maybe to destroy it. I don't know. It depends on what the skills are, but it could even be that maybe the rover evaluates that the rock is small enough so that it can go over, basically, okay? So it's this kind of autonomy that we'd like to be able to have, okay? And so what has been done in existing rovers is is, as you can see on this slide. And I take most of it from Perseverance because it's the latest achievements. And as far as I know, the most advanced actually deployed rover. Okay, so NASA ponders the term semi-autonomy in several of their documents. Okay, and so by semi-autonomy, what they mean, okay? And it's described in plainly in several of the documents, so it's really nice. Okay, it's that it's human planning. Okay, that's the robot doesn't plan by itself. Okay, so there is a team called the NAV team that has access to the whole data the rover has, but also satellite imagery and so on. And of course, they decide the science mission. Okay, so the goal, and for that goal, they build a plan. Okay, a plan can be a route. Okay, but it can be also a schedule of sampling data all around the route. Okay, is to activate the different science equipment to collect science on the way. Okay, and the role of the rover is to execute that plan. And this is where the autonomy starts, is that whenever there is a problem, an anomaly, so what the NASA calls hazard identification, then there are two scenarios. Is that in some cases, in some predefined cases, the rover will be able to deal with that automatically, so which is a great form of autonomy. And in all of the cases, it will just wait for humans to be planned for them. Okay. And so more precisely on Perseverance. Okay. So you can see on the right hand the picture. This is an actual picture that's provided by NASA about Perseverance. Okay. And so this picture shows what the team can see. Okay. So they have special tools. Okay. So some kind of VR goggles. Okay. They put on, and they can enter this virtual world where they see a 3D model of Perseverance, and the plan is the kind of lines you can see. Okay, the light blue lines that show the position that the robots will hold in the future and the past. Okay, and the white part is produced by a 3D camera mounted on Perseverance. Apparently, Curiosity didn't have such kind of camera. Okay, it's apparently pretty accurate. Okay, and it allows to expand the amount of autonomy that the rover has. Okay, so more concretely, in terms of system architecture, Perseverance has two elements. Okay, Curiosity had earlier versions of those. Okay, but I'm talking about Perseverance here. One is called Autonav. Okay, and so Autonav is for, I guess, automatic navigation or autonomous navigation, which really they ponder as a semi-autonomous. And I didn't know that recently. They revealed that they had this this phrase to describe the philosophy of the system, is that they call it thinking while driving. Okay, and apparently applying this thinking, okay, they can go. Perseverance can go now to 120 meters per hour. Okay, while Curiosity was 6 times slower. Okay, so that's pretty impressive. Okay, and so the Autonav is contains what we call a planning engine. Okay, and so this is one of the talk I had in I gave here in April, I think, where I talked about the Plexil software engine that is written by NASA for Curiosity and for a range of other robots. Okay, and is running also on Perseverance. Okay, so Plexil is you write down a plan, you give it to Plexil, and Plexil is going to execute it on the rover. Okay, and so Autonav uses Plexil and uses extra inputs like the 3D maps that it can build automatically, and a range of other sensors. And it uses all that to think while driving. That means to evaluate the situation. So, okay, so at each time it goes forward and continuously, it uses all that data to evaluate whether it's safe to continue. Okay. inside AutoNav, there is something called eNav. And sorry, I forgot what the E means, okay? But it's the subsystem where they have what they say algorithms and software specialized in hazard identification, okay? So that's a specialized component inside AutoNav. Okay. So when we see all that, we can wonder, okay, so is autonomous navigation solved? Okay, we have everything that we need. Okay, and so here are a few limitations. So sorry, I tried to it's pretty dense slide. Okay, but let's go through it. There are 2 points basically. It's about self-limitations and the specific case of perseverance. So the self-limitations is that in general we want to limit autonomy. And in system design, mostly is because of safety and reliability. Okay, that we can't service the robot on Mars. Okay, there is a problem, there is a bug or whatever, we just can't do anything. Okay? Safety is not so much a problem because it's not like we are going to have a traffic accident on Mars. Okay, but still we have safety for the system itself because it's very expensive and we would like it to do science for 10 years basically at least. Okay. And so correlated to that is to ensure more safety and reliability, usually we reduce the complexity. Okay. Because a more complex system has more chances just to crash. Okay. More chances to have bugs and so on. Okay. So it's like making some mechanics with a lot of moving parts that we don't need. Okay. Each of them can break. The third point is a bit obvious. Basically, it's a development cost. Okay. And here the cost is in money, but also in time. Okay. Because all that complexity to have autonomous software and so on to test, to have the compliance, software compliance, and other things like that would just make the project drag for much longer. And the last point is it's a software concept that is called YAGNI. Okay, so don't know whether you heard about that before. YAGNI means you ain't gonna need it. Okay, and so the thing that more autonomy than what NASA has done. Well, on Mars it's very hard to justify maybe for now because there is nothing. Okay, is that it's not there is nothing. It's a simpler environment than Earth because we don't have traffic, we don't have air traffic or road traffic and so on. Okay, there is no vegetation, stuff like that. Okay, so it's still obviously a complex environment, but it's much less complex in that sense. Okay, and so basically the hazardous things that we would need to deal autonomously, well, we can kind of enumerate them and just deal with them. Okay, and it's basically avoiding rocks and avoiding big slopes and stuff like that. Okay, so doing more complex than that is hard to justify as well. Okay, the second point is about perseverance in particular, and here there is a long extract from an official document, okay? And the bold part is more telling, okay, is that you see, they start with, of course, perseverance can't be on autonomous navigation alone. An entire team of specialists develops a navigation route and does something, okay? And just later, you see they justify because of the radio signal delay between Earth and Mars, they can't simply move the rover forward with a joystick. So this is to justify that some autonomy is needed. Okay. And so the entire team of specialists, once they have a navigation route, okay, they beam the instructions to Mars and the rover executes those instructions the following day. Okay. And so what's very interesting is that they are doing some AR, but not the AR we are talking here. They are doing actual augmented reality. Okay, is that they we can see from the previous slide with the image of the virtual reality, the environment they have to be able to evaluate the routes. Okay, it's this is where the autonomy and intelligence comes from. It's from their investment on augmented reality and virtual reality. Okay, and it's interesting, and actually, Meyer made me reveal that yesterday, in the sense that we can see an interest here, is that by proceeding this way, they solve two problems. They have some amount of autonomy so that the mission can go faster. Okay, the robot can take decision on its own and can on some scenarios and can just go ahead. And so, as you can see on this image, it means that there is a route, and you know, if everything is just fine, they know where the rover is actually physically. Okay, 50 minutes ago. Okay, 50 minutes late. Sorry, and they see what it's doing, but the robot is also collecting live images at a very high resolution right where it is, okay? And it's beaming part of this data right away. So it means that while the robot is moving, the team can use this virtual reality environment to also explore these very fine 3D maps and imagery that they get, so that during the mission, they can be super opportunistic. That if the rover passes something that is very interesting, they can just say, stop and do it, and check for that, basically, okay? And that's very interesting, especially in the discussion we have with David Lang about telerobotics, okay? Because the distance here, we have a bit of an extreme case, but how can we exploit this case, basically? And this is where autonomy comes into place, because autonomy allows us to exploit that case, in this particular case. Okay. So anyway, you see, it's in a way, it's fantastic, and it's working, and it's adding a lot of value, okay? But in a way, it's also very mundane, okay? That we don't delegate much to the robot. We are not at the level where we can just say, okay, go to the B spot to get some samples, okay? Because this is where we could maximize the time for the rover. It could even go faster, perhaps, okay? But also we can maximize the science time that the time that the time the team can dedicate to actual science, rather than just driving the rover. Okay. So the thing that I'd like to drill a bit more on the safety and reliability. Okay, because of the budget and there is no replacement part, basically. Okay, it must be perfect in a way. These are the most telling about the scope of autonomy. Okay, and so the positioning of teams like NASA is, of course, to me, one of the most advanced, but it's also relatively conservative because they can't fail. Okay, so there is no room for slack. Okay, but they do welcome flexibility. Okay, and this is where there is a data point I couldn't find, and I will ask you a question a bit later. Okay. But the thing is that when we look at the technology NASA has, okay, Perseverance is running something I mentioned called Plexil. Okay, it's a software that takes as input a plan and will execute it. Okay, it's a little bit like a Boss explained earlier. Okay, and so the plan is basically executing routines. Okay, routines is just to say, okay, turn the wheel for that many minutes for as long as the torque is within these values and so on. Okay, and we can see that as a set of rules. Okay, and so here I'm speculating on the kind of rules that NASA rover would do. Okay, but not too much speculating because I checked a few of their projects. Okay, that you can see in the middle of the slide an imagine rule is that if there is no obstacle detected and we are not arrived yet, then we go forward. Okay, else we stop and we report because maybe there is a problem, something like that. Okay. Another rule, okay, is to say, okay, if the rover is in the stopped state, it's not moving at all. Okay, and we have an obstacle detected, so we can infer that we are waiting basically for something to happen. Okay, and so we are stopped and we know there is an obstacle. Okay, so we can have a rule that say, okay, then we turn the head 10 degrees left or right, okay, and check again whether there is an obstacle, okay, and we repeat that and still we find no obstacle, and finally we can go forward. Okay, so it's a bit strange, but it turns out that a lot of programs are just that, and formal planning is about things like that as well. Okay, is to have rules that you can there are some programming language, but you can map them to basically if then else kind of rules. Okay. And so when we are using if then else kind of rules, this is part of what is called deductive reasoning. Okay. So deductive reasoning, to be very clear, it's the canonical example for deductive reasoning is to say, okay, it's the Socrates example. Okay, is that all human beings are mortal. Okay, and Socrates is a human being, so Socrates is mortal. Okay, and so in deductive reasoning there is no flackiness. Okay, there is no slack. If you have A that leads to B usually, and you observe A, you will get B. Okay, it's certain. Okay, and this is where there is a point that we are such kind of certainty can be very brittle in reality. Okay, so to ensure maximum safety, maximum reliability, and that's pretty generic in system design and very clear in software design. Okay, is that it's deductive reasoning. Okay, we don't take into account uncertainty. We are assuming certainty. Okay, and so if there is an obstacle, we will have a plan to say, okay, we turn the head 10 degrees. It's not 11, it's not 12 degrees, it's we turn 10 degrees increments. Okay. And so the thing is that why 10 degrees? Okay. So good engineers will make a lot of tests and say, okay, in our conditions in our environment, where the rover will be, yes, 10 degrees is a good compromise for such and such reason. Okay, we'll be very rational about that. But why, if there is a better way, why should not the robot be able to try that? Okay, and this is incompatible with the safety and reliability because it adds some capabilities that we may need. Okay, and so that's not super convincing. But anyway, let's try to push a little bit on that. Okay, because what I'm proposing basically is to go from deduction to abduction. Okay, and abduction in the meaning I'm talking about here. Okay, not the modern meaning. Okay, and so deduction is about rules to say if you have A, then you get B. Okay, and so the problem is that the problem for an autonomous agent is how to come up with these rules. Okay, because in engineering we dictate those rules. Okay, you say, yeah, if you see a rock, you stop. Okay. But can we have, or is there any mechanism that would allow an autonomous agent to come up with that rule in the first place? Okay, and so this is where I'd like to introduce. I will introduce a new mechanism, and the second one is abductive reasoning. Okay, but it does exist. Okay, and it's something that has been understood for quite some time already. Okay, is that how we make rules? Okay, is called inductive reasoning. In inductive reasoning, what's happening? And so I call that a solution level 1 because you will see that it helps, but it's not enough. Okay. Inductive reasoning is about making discrete observations. Okay, you observe the several things that are related. Okay, and you put them together to sum them up into a rule. Okay, and so to give you an example, it's something we do quite often. Okay, is that let's say that the rover, has some motors. Okay, and it uses the motor, it selects for some reason. Okay, power 4, and with power 4, it's on sand. Okay, and it will slip a little bit, and so it measures somehow that it has 3% of slip. Okay. And it's some data that it's logging today. Okay, but in the log there is also data from yesterday, where it was in similar conditions, and the motor power was 3.9, and there was no slip. Okay, and so you see we have the same pattern. Okay, we have some power for the motor that gives us slip or no slip. Okay, and if we summarize accumulation of this log data, we can make a rule. We can say, oh, if the motor power is above 3.9 on a sandy ground, then we will have a slip around 3%. Okay. So the mechanism that we are using here is called inductive reasoning. Okay. But you see, there is something missing here. Is that how do we make the observation in the first place? Okay. Because I'm talking about rules in the log. Okay. But they are in the log if the human engineer decided to put them in the log. Okay. And lets the rover use those log data. Okay. And so this is where we can go one step deeper. And this is where abductive reasoning comes into place, because abductive reasoning is about collecting just statements, facts, evidence, whatever we want to call them, and we have a soup of evidence, and to try to make candidate rules out of this soup. Okay, and so I can explain a bit more, but here is the title of the slide is from deduction to abduction and back. Okay, and now it's at the end back. Is abductive reasoning is about having a soup of unstructured facts. Okay, and by abductive reasoning, we are able to make some candidate rules. Most of them are just wrong or just bollocks. Okay, and then we go back to inductive reasoning, and we have all those rules. We have motor power 4 slips 3. Motor 3.9, no slip, okay, that emerge from the soup, okay? And by inductive reasoning, we can put them together in candidate rules, okay? They are still candidate rules because they have some certainty, some uncertainty, okay? And this is when we have mathematically what we'll call certainty, but in practice, that is almost certainty. This is where we are back to deduction, okay? And I hope I lost no one at this point. Is that all right?
Yes. Following along.
Okay, yes. And so you see, this is this loop that we could exploit, okay? And with, I think, clear benefits about the flexibility of the software. So there is a cost of complexity, but this is maybe how projects like a NASA project with a very strict schedule and maybe it doesn't fit their picture, okay? But we are not there, okay? So if I try, yep.
In the human design selection,
yes.
it's inductive, right? Basically, we are doing the induction for the rover.
So, sorry, it's a bit complex, okay? Because we are doing for the rover, we are clearly doing the abduction for them, okay? And we are doing part of the induction, okay? And so I'm getting a bit ahead, but this is where deep learning comes into play, okay? So to answer your question, is we are doing part of the inductive reasoning for them. It turns out that they are already doing part of it. And this is deep learning. Okay. I will talk about that in a couple of slides. Is it okay, Niraj?
Yes.
If I run away right now to answer later. Yeah. Okay. Okay. So just a quick. This is I think that was from Venkat's Twitter. So he liked an extract and something that reminds me this. Okay. Francis Crick, okay, so usually people know him, okay? So he wrote in one of his books that there isn't such a thing as a hard fact when you're trying to discover something, okay? It means when you have no idea, when you just have something you don't understand, whatever, there is no hard fact, okay? It's only afterwards that the facts become hard, okay? And this sentence is kind of summing up what I've just explained of going... the hard fact is the thing you can conduct deduction on, basically, okay? Because it has been, we are pretty sure that it's certain that if everyone is mortal and Socrates is someone, then Socrates is mortal, okay? This is a hard fact. But before that, it's a soup, and it's about discovering, okay? And a discovery is very relative, because we can have a general discovery of relativity, discovery of gravity, or stuff like that, okay? But a child is discovering stuff all the time, okay? So this mechanism of discovery is from an unstructured soup of facts and evidence up to, by some mechanism, up to hard facts on which we can react fast and take fast decisions, okay? So this is how I'm basically repeating what I said in text here with an image, okay? Is that we have some real world, okay? It's the cloud amorphous stuff on top here. And when we are designing rovers, okay, basically at some point we have sensors, okay, to interact with this real world, and in particular to digitize the signal so that we can do computation on it. Okay. So this is the second layer where we have raw digitized knowledge. And so this is what I've used the word evidence several times during this presentation. Okay. And so usually the raw digitized knowledge, you know, it's a set of symbols, okay? It's they are represented with rules, and this is usually where we can conduct deduction on, okay? And so that, you know, the sensor, there is a sensor that says there is an obstacle ahead, okay? So this sensor is on or off, okay? And so deduction, we say, okay, if it's on, we do that. If it's off, we do that. Okay, that would be a deductive rule. Okay. And so what I'm talking about here with induction and abduction is to add two other models. Okay, induction for rule making and abduction for explanation making. Okay. And so the arrows, I did not label them, but because it would be too heavy. Okay, but I will quickly explain. Okay, it's because this is where you have a parallel with the Boss system 1, system 2, and the subsumption architecture, okay? Is that when we go from the real world down, okay, is that we are going deeper and deeper inside the system capabilities, okay? And so when we have some sensory input, okay, we digitize it, and it's something we can we know how to act on, okay? We can use deduction rule because we know what to do, okay? So it will reach here with this, it will reach deduction rule box, okay? And if we know what to do, we just go directly to the real world through some actuators. But from the deduction rule, if we hit a situation we have no rule, okay? Most systems, they will just stop, okay? But here, when we have an induction engine, we can move to the induction engine to see whether we can use that event plus the raw digitized knowledge that we have accumulated so far. So it includes the logs and so on, okay? Can we use these two ones to create a new rule that maybe we are sure enough of that rule to elect it now as a deductive rule, okay? And so that will be the going back to deduction, or it's not good enough for deduction rule, but it's safe enough to implement, and so we go directly to apply it in the real world. And similarly, at induction, if we see that we cannot make a rule out of the soup that we are facing, now, then we go down to the abduction layer, where we have a similar mechanism, where we can maybe produce some inductive rule or not, and depending on that, act in the environment. Okay, and so when we see this picture, we can. I'm pretty clear that NASA's missions so far, okay, are covering the blue parts. Okay, so they clearly have deduction rules, and this is implemented in the Plexil plan execution engine. Okay, and but in a way, you know, they're using their augmented reality and virtual reality capabilities. Okay, because it's a lot of tooling. It's very impressive. Okay. And using this teleoperation approach, basically they don't need the induction and abduction because they are doing it themselves. Okay. And so here is related to Anuraj's question. Okay, is that I can't answer this question because I couldn't find any information about perseverance and curiosity to know whether or not they were using deep learning. Okay, But it turns out that deep learning is actually an implementation of induction reasoning. Okay, and so one easy way to understand that is that I explained that induction is about, okay, you have several rules that you see, okay, but it's the motor is at 4 and I got sleep. The motor is at 3.9 and I got no sleep. Okay, I have these random rules. Okay, but I don't get a compact generic version of that. Okay, it's exactly what supervised learning in deep learning is doing. So I'm not sure whether you're familiar with that, but in supervised learning, okay, what we do is that we take, for example, images. We take many images, and for each of these images, we say something that is relevant. So, for example, if we want a cat finder, okay, to create a machine learning that will tell us whether an image contains a cat or not. Okay, so we take all our images, and for each image, we say there is a cat or no cat, and a cat or no cat. Okay, and deep learning is about taking the supervised learning. Okay, is about taking these images and these annotations, okay, and we take the image as input. We will produce some output. We compare that output with what we expect. Okay, the output is no cat, and we compare whether it's true or not. Okay, and if it's true, great. If it's not true, we tune a little bit the machine learning algorithm to make it answer correctly the next time. Okay, and so as you see, each of these pair, this image cat, this image not cat, all of those ones are small rules, and machine learning algorithms in supervised learning and mostly deep learning now, but it's just a special case. Okay, they are just doing that. They are taking all those examples to try to approximate by induction a generic rule. Okay, so generic rule, deep learning is in some cases it's called a function approximator. Okay, and that's it. Okay, is to approximate the function to say if I input an image as output, I get 0 or 1. 0 means no cat, 1 means a cat, basically. Aniraj, does it explain more of what you wanted to know?
Yes. So in this deep learning, supervised learning, by annotation, you mean labeling the data set, right?
Yes, that's right.
Yeah.
Yes. And so I'd like to close this parenthesis, but happy to come back to it. Okay, I think it's interesting. Just what I wanted to say on this slide is that I couldn't check whether NASA has deployed any deep learning algorithm or machine learning algorithm on Perseverance in particular. Okay, but if they did, then they are covering parts of induction. Okay, it's induction based on deep learning technology, which is very powerful because it's automated. Okay, so here it's one of the last slide. It's about the state of where I am. Okay, and also together with Meyer. Okay, so on the raw digitized knowledge. Okay, about producing raw evidence. This is what we're working on actually the past 3 weeks with Meyer. Okay, and we have we have engineering to do basically to be able to do that correctly. Okay, and so we have two parts here. Is a driver. Okay, it's a software driver to be able to run on the Hexabot to extract the data we want. Okay, either more. We could get some data already, but we would like to be able to streamline that. Okay, so that's why Meyers is starting to work to write a driver for that. And the second part is a data clustering algorithm. Okay, so it's about how to get the sensor data, the raw sensor data, and to try to start summarizing up into concepts that we can use in rule making at a higher level. Okay. And so the kind of, the rendering is not great. There is kind of gradient colors. Okay, this is proportional to my estimation of where I am toward my goals. Okay, and the last thing is that it's the note on the right is that I have some wiring about with the arrows and so on. Okay, but it's a kind of the way I see it now, but it's pretty classical way of seeing it, and I think it's going to change. Okay, I have several ideas. It's just to give you an idea of how it looks, but this is going to change, I believe. Okay. So some closing notes, because I see that, sorry, it's been pretty long, okay? Is that, it's how much autonomy to give a rover, okay? Because that's a question we have to keep in mind, okay? Is it really, what I'm doing, is it really useful for the project in a way, okay? And so I have this kind of equation that I call the Tini equation, when I say that the autonomy level you need is proportional to the inverse of the distance, meaning that we need autonomy when it's far away, okay? If it's close to us, well, a remote control and a tether is much more clever and faster, okay? And so I call it the Tini equation because it's like a teenager, okay? It's when you have a teenage child, step by step, that child wants to become more and more autonomous, okay? And also, on the scope of autonomy, I don't think to me, it doesn't include goals. I mean, I don't see goal autonomy as being something very useful concept, okay? So basically, the rover driver decides the goal, okay? And after, the scope of autonomy here is about how to reach that goal under good conditions, managing battery time and so on, okay? So autonomy is not for all scenarios, okay? And, in many cases, deduction is just fine, okay? So here, I'd like to push on abduction in particular and to extend induction beyond deep learning, okay? And I mentioned that maybe it was not NASA the best place to do that because they are really on very specific budgets, okay? But on our project, that feels like the right place and the right place and a kind of interesting, kind of maybe not unique, but a kind of unusual capability we could bring about, basically. Okay. So just to close this talk, something from the Douglas Adams. So I don't know if you know him, but interesting writer. Okay, but he's talking also about Sherlock Holmes. Okay, and about playing with these words like impossible, improbability, and so on. Okay, and so I like this sentence. I won't read it, but it's there for reference if you're interested. So sorry, I'm done talking. Sorry, I just realized it was pretty long. I hope it was interesting and happy to answer any question.
First of all, thank you. But I have a question about abduction. Earlier, you said that abduction was for generating rules, and here you talked about it for generating explanations. Can you consolidate the two?
Yes, yes, I can. So the thing is, so it's a bit of terminology used here that may not be the best choice. Okay, is that a rule is already something a bit formalized. Okay, or it's at least a candidate for formalization. Okay, an explanation, I see it as something that is much more flexible than a rule. Okay, in the sense that for a given fact, okay, is that for example, the grass is wet. The grass is wet? Yes, we can have many explanations. Okay, but usually we want to come up with a rule. Okay, so that's why I use the term here in terms of for abduction. Okay, the goal is really to have some explanation. Okay, because it's at a higher level. So in induction or deduction, this is where we evaluate what explanation becomes the rule, basically. Okay. So to give you an example, is that if you've already tried to, for example, I don't know, to bake bread, okay, is that you make bread every day and you get some flour, you get some yeast and stuff like that, and so you have your facts, your evidence, okay, about what you do, and one day you will mix the ingredients and you will succeed to make a bread that raises well, okay, and the other day you think you're doing the same, but no, it won't work. And maybe just because the temperature of the room is higher, okay, that can kill your yeast, okay. And so this is where at that stage, when we're still exploring, this is just a possible explanation, okay. This is why I use the word explanation, okay. And induction is more formal already. It's more like we have knowledge, okay. We know that will happen if I do this, and that we have already more structure, okay, and we already have rules, okay. In induction, I call them candidate rules, and in deduction, rules. I try to be consistent, hopefully, on this one. Meyer, is it satisfactory answer?
Yeah, we have to start building these rules in order for us to see what it actually means.
Sorry, what do you mean? To start building the rules?
Yeah, in other words, we have to actually try building rules using induction and using abduction and see what it actually means.
In what context? Sorry.
Learning by.
I mean force? Okay, yes. Okay, yes.
I have one quick comment. Is there some echo? Okay. When you use deep learning and abductive reasoning together, and especially in the context of the Dirk Gently versus Sherlock Holmes quote, which is also one of my favorites, I think what you're going to get is an unstable ontology. And by that, I mean, when you and I and in this group, we talk about Mars, we use the same set of proper nouns to talk about Mars, like, rover, rock, pat, goal, and things like that. And one of the things that happens when you use deep learning is the internal representations, what are called latent spaces of these deep learning algorithms, they seem to come up with their own representations and sort of proper nouns for talking about the environment they're in. And one of the interesting effects of that is you may end up with candidate rules in the abduction layer that are framed in terms that are not actually recognizable to humans. So they stop becoming explainable. So you and I might be expecting rules of the format under such and such conditions of motor slippage, increased power, right? So we're talking in terms of concepts like power, slippage, and motor. It may come up with like completely unrecognizable concepts like, squeaky noise is one noun, and even that's actually too legible. Maybe it's something like X, Y, and Z, and the rule could be something like whenever X exceeds Y, turn off Z. And X, Y, and Z are nouns we don't understand at all. And I think if you open that up, you get much more powerful solutions. And I want to connect that back up to the Dirk Gently versus Sherlock Holmes ones. The quote that you mentioned, it's actually the basis for a whole essay on, I'll send you the reference. I actually referenced it somewhere, but it's called The Games Afoot, Predecessors and Pursuits of a Postmodern Detective Novel. And it's by a researcher called Kathleen Bellin, and it's in the book I have. And she talks about how between Sherlock Holmes and Dirk Gently, the classic fictional detective went from basically what's called ratiocinative detectives who think in terms of stable ontologies. They do not seek supernatural explanations, for example. And what happens when you get the Dirk Gently style of detective reasoning is that the ontology opens up, and Dirk Gently is willing to solve mysteries using concepts that are basically inadmissible in a Sherlock Holmes solution. So in a Sherlock Holmes solution, you would not introduce things like time travel or ghosts or weird things like that, whereas in a Dirk Gently solution, you would actually allow those new ontological elements to come in. And I think this is actually a very fascinating thing to try and engineer into a rover, where the rover is not even setting its own goals. That's actually kind of uninteresting because you can game it. You can give it a sort of broader game in which it can set its own goals. But if you can actually allow the rover to make up its own concepts, which may or may not be understandable to humans, and come up with effective solutions to its problems based on those completely alien concepts, then you have a true rover, in my opinion. It's like an explorer that comes up with an ontology of things that get at efficient representations that we may not even have thought of, right? Maybe the right way to think about Mars environment is not even rocks and minerals and holes and things like that. Maybe the right ontology is completely different. And I think this architecture would actually open that up. And that's sort of the reason to pursue it, where you allow this kind of open-ended ontology building to happen.
Yeah,
What
thank
was
you
the
very much,
name of
Venkat.
what was the
Yes,
name of
please.
the book you mentioned?
I'll
Venkat.
post it. Hold on.
Thank you.
It's very hard to find. So what I'll try and do is I'll try and make a copy of the paper. I have a paper copy of the book, and I'll post it. But the reference is it's a paper in a collected series of papers in a book. Yeah, I posted it in the Discord.
Thank you. About your comment, Venkat, so thank you very much. And so the good news is that this is where I'm going personally, okay? And this is on this slide, the data clustering, okay? This is it, okay? So first, in the frame of this presentation, my goal was more to show the potential value of abductive reasoning for rovers, okay, and also perhaps to introduce this notion for people who don't know, because I think it's pretty fun as well, okay, and you know it's in the context of Sherlock Holmes and Star Trek and so on, okay, it puts a lot of things in perspective in a way, okay. But so about concept creation, this is exactly what I'm trying to do with the data clustering, okay? Is that, and also, so that's one aspect. The other aspect is about my questioning about what it means to go forward, okay? Is that we can, you mentioned about looking at basically the perspective, whether we are inside or outside, like in your CAD program, okay? From the perspective of the rover, going forward means something, but from outside, it's pretty stable. For all of us, we will interpret something as going forward in basically the same way, okay? But my question is, how does it happen inside the rover, okay? And so it's about what is the concept of going forward for a rover, depending on its body, okay? So these notions are related, okay? And here, concretely, this is what we have been trying to do with Meyer for 2-3 weeks, okay? Basically, I frame it. Meyer, tell me if I'm mistaken about the word I'm using, but usually I talk about situation awareness, okay? Is what I mean by that is about the capability to use raw sensor data to create concepts that are useful in the scene where we are, okay? So concretely, I mean that if the rover is in Meyer's garden and there is this high grass, okay, that stick to the legs and so on, that's a concept that we would like the rover to be able to capture, so that it will be maybe deciding and not to get too close to them, otherwise it won't be able to accomplish its mission, okay? And so I explain it like that, but in terms of conception inside the rover, basically what I'd like to do ultimately is to have it build its own story, build its own concepts, to be able to really be autonomous in that way, okay? And that may sound scary to make some kind of monster that does whatever, okay? So this is where I fall back on my legs and saying, okay, I decide for the goal, and this happens inside the rover. Outside the rover, it's a black box, basically.
I just want to say that if I put together everything we spoke about, maybe the rover doesn't have a concept of what you call forward. And then the question becomes, how do you communicate with the rover that created its own ontology? It doesn't see rocks. It doesn't move forward. How do you talk to it? I don't have an answer, of course.
Yes, I don't have an answer to that either at this point. But yes, it's completely related to that.
All right. So 11:30.
Yeah. Yes. Is there any last question, or I'll be on Discord after, so if there's interest.
So you
I'm
mentioned
going to have some. I'm going to have some questions, but I'm going to think about it for a while.
you had mentioned, Eric, that these abductive reasoning has been used on some robots. Or
So
has
yes, it was a very long time ago. Okay, and so I could dig out some information about that. Okay, I think it was in the late 80s or the mid 90s. Okay, but it may have been actually way before. Okay, my memory is bad here. The thing that abductive reasoning is really not new. Okay, it's the end of 19th century, and in the early ages of AI, so we are talking 50s, 60s. Okay, there were already discussions about that because it was already formalized. Okay, but I think it's pretty hard to see the value of that until recently. Okay, because you see, most of the software we've been writing software so far is basically implementing some kind of rule. Okay, that if you press the button, you have a pop-up. Okay, stuff like that. Okay, it's deductive, mainly deductive, and inductive reasoning has become really more present in the mind of engineers thanks to deep learning. Really. Because deep learning, we talk about deep learning in particular, but the thing is that deep learning is basically a statistical tool. Okay, that already existed. Okay, but they were not so well spread. Right now, I can see several projects where deep learning is a bit out of reach or too expensive to use. Still, the people are introducing statistical components, and so statistical components, in that sense, sorry, okay, it's a bit restricted sense. It's about rule making, like deep learning does. Machine learning in general. Okay, and so it was mainly deductive for a very long time. Recently, we have more and more inductive, and I'm not surprised that abductive is still out of reach. Okay, because I don't know, maybe because there are not so many business cases yet that would take advantage of it, basically. I'd like to thank everyone for your time. I hope it was interesting, maybe a bit entertaining and so on. But I'll be available to answer any further question and to expose other aspects if you're interested. And Anuraj, I will try to find some references about early robots that were implementing abductive reasoning inference.
Right. Thanks, Eric. And next week is Victor. So you ready